So we've talked about the birth, the lifetime, and the death of stars. And so I wanted to spend just a little bit of time talking about black holes because they're really interesting. And as far as grade 9 goes, grade 9 science, we get to talk about these things, and it's just too good not to take this opportunity to talk about something that's just so interesting. So we're gonna take this lesson. We're gonna talk about black holes. So a black hole is a region in space where gravity is so strong that not even light can escape. Okay. Scientists estimate that there could be millions or even billions of black holes in the Milky Way alone. So that's in our home galaxy, and there could be tons of them. Now, they're not nearby. They're pretty far away. But this is kind of what astronomers are estimating, millions or billions, which is pretty cool. Let's talk about kind of the anatomy of a black hole. Its boundary, there's kind of this boundary around a black hole. We call that the event horizon. Okay? And it's sometimes the event horizon is the point of is kind of called the point of no return, because once you pass over this boundary, nothing can get out. So nothing can escape. Now, it's not a line. It's basically an imaginary kind of it's an imaginary line in space. Like there's nothing there at the event horizon. It's just the point at which, you've gotten a little bit too close to the black hole, and now you won't be able to get out. So now you're in it, and nothing can escape it. Nothing. It is important to note, when we're talking about the anatomy of a black hole, we're talking about models, right? Like, yes, we've taken a picture of a black hole. It has been confirmed. The best model that we have is given to us by a kind of math and science called general relativity that kind of Einstein came up with a long time ago. But you have to remember that these are models, and so we have an evolving picture of what a black hole is. And for right now, the best model that we have is general relativity. And so general relativity would say that at the center of a black hole, there's a singularity, okay? And this is a point in space that is infinitely small and infinitely dense. So it's a teeny, teeny, tiny, infinitely small point that has an infinitely large density, right? So that means its mass is huge. Its volume is really, really tiny to give us this infinite density. At the singularity, though, space, time, and the laws of physics don't apply. These things kind of, as we understand them, space and time kind of break down. And the laws of physics don't apply in this model of what a black hole is. Which is really bizarre, and it's really one of those crazy, weird things, and we're trying to understand it. We're trying to learn more about black holes. There's a couple types of black holes. The first kind is probably the most common, and they're called stellar mass black holes. And these are the types of black holes that we've talked about before in a previous lesson, right? The mass of these is less than kind of 40 times the mass of the sun. So these are the smallest type of black holes. And this is what happens when a massive star goes supernova and then becomes a black hole. That's why they're called stellar mass black holes, because they're the remnants of these kind of dead stars. Okay? Most common, the closest one is V616 Mon, and it's about 3,400 light years away. So it's really far. It's really far. It's the closest to us, and it's still in the Milky Way galaxy. But it's really, really, really far from us. Okay? The other kind of black hole that's pretty well known are what we call the supermassive black holes. These ones have masses that are kind of like millions or billions times the mass of the sun, right? So stellar mass black holes are pretty much up to about 40 times the mass of the sun. These supermassive black holes, these are like millions or billion times the mass of the sun. Like, they're really, really big. And they're usually found at the center of a galaxy. And that's true for us too in the Milky Way. We're still not sure how they form, because given the age of the universe, even if a whole bunch of black holes, like stellar massive black holes, kind of combine together, we're still not sure how these got so big. There's some theories out there as to why, but we're still not really sure kind of where these supermassive black holes came from or how they got so big. However, probably the best example is Sagittarius A star, and Sagittarius A star is 4 million times the mass of the sun, and it's found at the center of the Milky Way galaxy. So it's right at the center of the Milky Way, and all the stars kind of in the center of that Milky Way galaxy, they revolve around it. And because the whole galaxy is revolving around the center, really kind of, you could say everything's kind of revolving around this. The last kind of black hole, the reason I put it in the chart is because maybe you'll notice, we've got the stellar massive black holes. They're less than 40 times the mass of the sun. And then you get the really, really, really big ones, the supermassive black holes. Well, what about everything in between? Those are called intermediate mass black holes. And this is what's so interesting about this field of astronomy, like this field of science, is that really we only found evidence that these existed. We only saw evidence that they existed in 2020. And depending on when you're watching this, that's not that long ago. These were detected by LIGO, the Large Interferometer Gravitational Wave Observatory. And because two black holes in space merged, they gave us evidence of an intermediate mass black hole. Okay? There's no really common examples yet, but this is the first evidence that we had ever seen that these intermediate mass black holes existed, which is really interesting because we couldn't find them. We couldn't see evidence of them. So this was the first evidence that we saw. So, we just talked about LIGO and how it detected this. It makes sense to kind of talk about, okay, well, what are the best ways of kind of looking at black holes? Like, how do we see them? Some of you may know that a couple years ago, we were able to have the first image of a black hole. And that was captured using the Event Horizon telescope. But what are some of the ways that we detect black holes? Well, first, this is the problem. They emit no light, right? So they can't be seen. It's not like we can go and look at a star through a telescope because a star can be seen. It's giving us light. All that astronomers can do is to observe the effect that a black hole has on nearby matter. So we can watch the stuff that's around an area and we can see what happens. So there's two things that we look for. Around a black hole, very often, there's what we call an accretion disk. And in this diagram, this is kind of like the accretion disk. Here in this diagram, this is like the accretion disk. It's basically a disk of swirling hot gas, right? So it's kind of like a cloud of hot gas and particles, and they're all in orbit around the black hole. So we can look for accretion disks. We can very often see that, okay? Also, we can look for quasars. Quasars are these jets of particles, and you can see them in the two diagrams that we have here. we can see like these jets that are streaming out of these black holes. Now, it's important to note that these jets of particles aren't coming from within the event horizon. These are jets, you can kind of see in the diagram here, these kind of swirling, this is an artist's interpretation, of course, but these kind of swirling gases. This is because of the magnetic field that the black hole has. And so the event horizon for this black hole would be somewhere in here. The event horizon would be somewhere in here. So these gases, like the accretion disk, this isn't from inside of the black hole. Inside of the black hole would kind of be in here. So it's not like the black hole is spitting out these particles. These are all particles that kind of come from all around, and they're orbiting, or they're around the black hole. So these jets, it's not like the jets are coming from inside here and being shot out. They're not, because that would be a contradiction. We know that nothing can escape a black hole. But these jets of particles blast away, guided by these really strong magnetic fields. And we can use both of these things as evidence. Okay? There's lots of other things that we can do, like we can image stars that are kind of close to a black hole, and we can watch the stars moving around it. That's how one of the most recent Nobel Prizes in physics was because of monitoring the stars around Sagittarius A star, and that's kind of what gave us this idea that, oh, that's probably going to be a black hole there, because there's nothing that we can see that's in that space, but there's all these stars that are orbiting it. One of the ways that we determined Cygnus X1 was because of these quasars from Cygnus X1, and that was another black hole that we discovered. All these really, really interesting things you'll learn more about, hopefully, when you take grade 12 physics.